All right, so the next quadric surface we're going to graph is something that we'll see is called a hyperboloid of two sheets. The term hyperboloid indicates that the cross sections or the traces that we're going to look at are hyperbolas. And we'll make sense of this two sheets thing once we see the surface. It'll make more sense once it's graphed. So, same idea. What we want to do is look at traces. And again, my approach is to not dump a ton of time into finding those traces where x, y, or z are equal to something other than 0. Typically, it's enough for our purposes to just look at the coordinate planes themselves. So this guy, this equation is already in that kind of standard form that I want it to be in. Compare that to the ellipsoid case where I had to divide everything by 16 first and add that constant over. This is the way that I want it to look. So let's start by looking at the xy plane. In the xy plane, this guy here, remember what we want to do is plug a 0 in for z. So that equation that we're going to be graphing is going to look like negative x squared plus y squared over 4. Or, written a little bit more conveniently, y squared over 4 minus x squared equals 1. And in fact, I can put that x squared over 1 as well. That tells me where my vertices and co-vertices for my hyperbola would be. Okay. Now, for these quadric surfaces, we're honestly not looking for incredible accuracy. If you remember in conic sections, when you're graphing conic sections and you're doing a hyperbola, you're taught to use the denominators here. So my y, for example, I'm going to get plus or minus 2. Square root of 4 is where I'm getting that from. My 1, I get plus or minus 1. Negative 1, positive 1. You're taught to do this box like this. And then whichever variable is the positive one, so the y in this case, my hyperbola is going to open in that direction. And the purpose of this box is actually to create, like, asymptotes through the diagonals of that box. We're not going to worry about that level of detail here. The idea is just to make sure that we have our hyperbolas with the correct vertices, so at 0 plus or minus 2, that's where I have them, and then that they're opening with the correct orientation, in this case about the y-axis instead of about the x-axis. So I'm not going to continue using this box thing anymore. We don't need that level of detail. All right, so next up, let's check the xz plane. So now I'm plugging in a 0 for y, okay? And what's going to happen in the xz plane? Well, this is an interesting case because if I plug a 0 in for y, then I'm going to have negative x squared minus z squared over 2 equals 1, okay? But this isn't the equation of a hyperbola. If it were the equation of a hyperbola, then I would need one of those two terms to be positive. I can't have minuses in front of both of them. So you look at that and you might think, well, what if I just, multiplied both sides by negative 1? Wouldn't that take care of that issue? And no, because now you're going to have a negative on this side. This, it turns out, has no solutions, this equation. Think about it for a moment. If both terms are negative, notice it's an x squared and a z squared here, by themselves, those would both be positive, but by putting negatives in front of them, I am guaranteeing that this side of the equation is either a negative number or at best 0 if x and z are both equal to 0. That means there's no possible values for x and z that I could plug in here to ever get a positive number like a 1. So this provides no graph whatsoever. And this will create a separation in our graph, which is going to give us those two sheets that I've mentioned up above. So there's no graph here. It's just blank. Okay, now let's take a look at the YZ plane, the one trace we haven't investigated yet. One thing I should mention is that if we looked elsewhere, aside from just the xz plane here, but if we looked at, for example, planes that are parallel to this coordinate plane, like y equals 1 or y equals 2 or so on, notice that's going to create a constant here which, depending on the size of that constant, will resolve that issue of having no solution here. But we'll kind of think about that a little bit later once we have a graph to look at. So yz plane now, I'm plugging a 0 in for x, and that gives me this equation, y squared over 4 minus z squared over 2 equals 1. Okay, and again, I'm not going to bother drawing the box to get a perfect hyperbola. What matters here is that I have the correct orientation and the correct vertices. So my y squared term is the one that's positive, and that means I'm going to go out as far as positive 2 and negative 2. My hyperbola should be opening about that y-axis, like this. Okay. Let's turn this into a surface now. So if I come down here and I create my x, y, and z axes, so x, y, z. Let's think about where these traces live. So let's start with my xy plane right here. I have this hyperbola that should open along the y-axis. So focusing on my xy plane, we have y-intercepts at positive 2 and negative 2. And it's going to open kind of like that. Okay? The xz plane, remember, we don't have anything there. The surface never intersects the xz plane. Well, that's what that basically means for us. But moving on to my yz plane, here's my yz plane. Again, it looks similar. You know, we have y-intercepts at plus or minus 2, and it opens along that y-axis. And so we're going to get something kind of like this. See if I can kind of go like that. Kind of like this. Okay? Now, my graphs, as usual, don't look great. But if you think of the surface here, and if we were to do more of those cross sections, you're going to see that this thing kind of has this, you know, it kind of, I almost want to describe that as like a bell shape. Something kind of like that. Okay? So notice how there's two separate parts of this surface. They're not connected, but they open in opposite directions. That's the reason we call this two sheets. The term sheet here is like another, way of saying surface. Two independent little pieces of the surface with some symmetry about the origin. But you can see that no part of the surface crosses through the xz plane. That's why we had this blank coordinate plane right here. Now, if I did start looking at some of the traces that are parallel to the xz plane, then what I would need is to plug in values of y that are greater than or equal to 2. And let's think about why that's the case. So I'm going to maybe off to the side here. Let's plug in a value k. Let's just call it k to keep it general for y. Negative x squared plus k squared over 4 minus z squared over 2 is equal to 1. Now if I multiply everything by negative 1 so that these two terms become positive, and then if I add this term over here, I'm going to get x squared plus z squared over 2. Multiplying this by a negative makes it negative, and then adding it over there makes it positive again. K squared over 4 minus 1. That's what I would have. Okay? In order for this equation to have any solutions at all, we see that this side needs to be greater than or equal to 0, because that's definitely true of this side. But that won't happen until k is either greater than 2 or less than negative 2. And that's why, again, not only do we not have any part of this surface passing through the xz plane, we have all this additional space along any trace parallel to the xz plane where y is between negative 2 and positive 2. However, if we do eventually start using values of k that are greater than 2 or less than negative 2 so that this is positive, then dividing both sides by that positive number, whatever it happens to be, reveals that we're looking at the equation of an ellipse. And that makes sense given these shapes. If I were, for example, to take the plane y equals 3 and look at the trace there, notice the shape that I have does create sort of this elliptical cross section there. Okay, so that sort of gives us an indication as to what those cross sections or those traces would look like. But again, hyperboloid of 2 sheets is what we call that. So let's take a look at this table. This appears in your book, and it's a table of the 6 basic quadric surfaces that we encounter. These are all what we would call non-degenerate cases, and we're not going to really spend any time talking about the degenerate cases. But we've looked at some of these. So we've looked at an ellipsoid, we've looked at the hyperboloid of 2 sheets, and the hyperbolic paraboloid. Here's 3 that we have not looked at yet: a cone, an elliptic paraboloid, and a hyperboloid of 1 sheet. In this table, you're seeing the sort of the standard equations in each case. And they all look very similar, but it's helpful to kind of think about their differences so you can see why different equations lead to different surfaces. One thing that I always like to look at with these equations is whether or not the origin should belong on the surface. So for example, in the case of an ellipsoid, the ellipsoid does not have the origin on the surface. For this ellipsoid, the origin is at its center, but it's not on the surface of the ellipsoid. And that would translate to the equation by thinking in terms of plugging zeros in for x, y, and z. Remember, the origin is where x, y, and z all equal 0. And you could see that if I plug 0 into all 3 variables here, I'd get 0 equals 1, a contradiction. So that would mean the origin is not on that surface. Compare that to the equation for a cone. Z squared over c squared equals x squared over a squared plus y squared over b squared. If I plug x, y, and z, or if I plug in for x, y, and z a 0, then this reduces to 0 equals 0. That's true. So that would indicate that the origin does belong on that surface. And you can see how the cone has this point at the origin here. Oh, excuse me. So sometimes that's like an easy point to check to help rule out, one of the surfaces that doesn't belong. You can see in the case of the elliptic paraboloid, the origin would be a solution here. Notice the elliptic paraboloid has a very similar looking equation as the cone, but the z and the c are not squared here. Hopefully you can see that by plugging in a 0 for either your x or for your y, this equation reduces to a parabola, the equation of a parabola in 2 variables. So, I'll leave it to you to kind of like look at the equations and see not only, does the origin belong to that surface or not, but also confirm by plugging zeros in for different variables what the traces would look like in each of these different quadric surfaces. Okay, so almost done here. I have one more example that I want to do. We're going to graph one more surface, and again, this one's not in that standard form yet. And this one is just to point out something that happens with quadric surfaces that also happens with conic sections. All of these quadric surfaces that I have here on this table are in some sense centered at the origin. Now the term center isn't always the appropriate term to use. For example, this elliptic paraboloid, I would say that it has a vertex at the origin, but they kind of represent the simplest case, where the origin is sort of a center or a vertex, or it provides some symmetry there. In the case of conic sections, when we look at more general equations for those, we see that those conic sections can be shifted so that they're not centered at the origin, or they don't have a vertex at the origin. And that's what's going to happen in the case of this example. I think this example is also straight out of your book as well, but let's take a look at how to deal with this. So the first thing I want to do is notice that I have terms here that are not squared. I have an x and a y, as opposed to an x squared and a y squared. This, we're going to use a technique that you've done with conic sections, and that's completing the square. So I'm going to group up my x terms, x squared minus 6x here. Group those up and leave some space. I don't need to complete the square with my y because there's no y squared showing up anywhere. So I'm going to leave that alone, but let's deal with the z's as well. Plus, well, there's no z term that's not being squared anywhere, so I also don't really need to worry about that. So let's do let's just call it 2z squared minus y. And then I'm going to subtract the 10 from both sides, equals negative 10. Okay. Next thing I want to do is complete the square in the parentheses here. So half of the linear term is negative 3. If I square that, I get plus 9. And I need to add that to both sides. So this is going to factor down to x minus 3 quantity squared. Then I have plus 2z squared here, minus y equals negative 1. Okay? Now what I'm going to do is try adding this y over to both sides so that I get x minus 3 squared plus 2z squared equals y minus 1. And then finally, if you were to look at all of the standard equations here for these different quadric surfaces, none of them seem to have a coefficient in front of any of the terms, you know, z or x squared or y squared or what have you. We do have denominators which technically also form coefficients, but I guess what I'm getting at is that this 2 here is a little problematic. So I'm going to divide everything by 2. That's going to give me x minus 3 squared over 2 plus z squared, let's call it z squared over 1, equals y minus 1 over 2. Okay? So the next thing I want to do is look at this and compare it to my table of quadric surfaces to see which equation it appears like we're looking at. And what I want to do is temporarily forget about anything that's being added or subtracted to an x or a y. So compare this to, for example, compare to x squared over 2 plus z squared over 2 equals y over 1. Notice that's not the same equation as this, but we're going to see how to take this guy and turn it into this guy right here. So on this side, on the left, I have 2 of my variables that are being squared. Both terms are positive. And then on the other side of my equation, I have the third variable that is linear. It's not being squared, and it too is positive. What does that look like over here? Which equation does that resemble? To me, it looks like this elliptic paraboloid. Notice on my elliptic paraboloid, I have 2 positive terms, both being squared, and on one side of the equation, those are added together, and that's equal to the other variable not being squared on the other side of the equation. The only difference, though, between this equation and what I have there is that it's the z that's appearing as the linear term here, whereas it's the y that's appearing as the linear term here. What does that do to the elliptic paraboloid? All it does is changes its orientation. You notice how this elliptic paraboloid is opening kind of about the z-axis. It's sort of swallowing up the positive z-axis here. What's going to change in our graph is that this elliptic paraboloid is not going to open upwards in this way. It's going to open along the y-axis. Okay? So for this, I'm not going to worry too much about getting the correct vertices and everything. I just want a general idea of what this graph or this surface looks like. So I have my x, y, and z. We're going to have an elliptic paraboloid that opens along the positive y-axis. So it's going to do something like this. Okay? Don't worry about being too perfect with your graph. Obviously, I'm not. That is the graph of this guy. It is not the graph of this guy. How does this come from this? Well, just like in the case of quadratic or conic sections, the -3 here and the -1 here correspond to translations of this elliptic paraboloid along the x and the y axes, or in the x and y direction. In particular, we're going to move our elliptic hyperboloid 3 units in the positive x direction and 1 unit in the positive y direction. What does that look like? Okay, so we're going to have this x, y, and a z here. So again, I'm going to move 1 unit in the y direction. That's like this. 3 units in the positive x direction. 2, 3. Okay, that's going to take me to this point. This is the point 3, 1, 0 right here. That point is what happened to the vertex of my elliptic paraboloid. It was moved here. But aside from that, it's still going to open in essentially the same way. It's still going to look like this. Okay, so this is just a translated version of that surface. And that's how we deal with these more general cases here, where it's not just x squared or y squared or whatever. It's you know, x minus 3 or x minus y minus 1, what have you. Okay, that's about it. That's all the time we really need to spend on quadric surfaces. Just so you know, the most important thing from this section to walk away with is sort of a sense of what kind of a surface we're dealing with based on the equation. A general sense. It doesn't need to be, you know, perfect. We don't need to be able to freehand these surfaces super perfectly, but it will matter in later sections, in particular chapter 15, 16, a little chapter 14 as well, that we can look at an equation like this and think, okay, that's an ellipsoid, and with that comes some intuition about what that surface generally looks like. Okay, but that's going to be it for 12.6 and all of chapter 12.